In this video, I am going to derive this equation here, and this is known as the time dependent. So it's time dependent, not time independent. There is a time independent, which I will go through in future videos. So time dependent Schrodinger equation. And I should probably put derivation in scare quotes because it's not sort of a true derivation. I can't spell and talk at the same time. Derivation. It's not a true derivation, but it's something that will take sort of simple, well-known concepts and from there turn it into this equation right here. And we'll get a little bit of understanding just from doing this exercise about what all these symbols mean. But in a future video, I'll go into more detail, sort of digging into each of these symbols and talking about what they mean. But we'll start here first with this derivation of the Schrodinger equation. And so the first sort of simple thing we can start with is, I think this is called the Planck-Einstein relation, something similar to that. So that's just the energy is equal to the Planck constant multiplied by the frequency. And so this is telling us that the energy is some multiple of this constant here, which I believe is something on the order of 6.626 times 10 to the negative 34 joule seconds. So it's a very, very tiny amount of energy. And so energy is a multiple of this multiplied by the frequency, which will have units of 1 over seconds, resulting in those canceling out. So we have joules here. But then you will often see this written with what's called the modified Planck constant, which uses the h bar, and that is just h over 2 pi. And so this is telling us that we're using sort of an angular or circular sort of idea for this h. I said in a previous video that you could almost think about it like the units are joule seconds per radian, if you will. And we will also then change the frequency into what's called the angular frequency. You'll often see this written as an omega symbol. I tend to use this nu symbol, but that is going to be the frequency multiplied by 2 pi. So we can see that hf is equal to h bar nu, since h bar nu is just 2 pi multiplied by our frequency multiplied by our h, which is divided by 2 pi. And so those will cancel out, and so those are equal. And this, as I said, is just telling us that the sort of the takeaway that the concept here is that the energy of a photon is quantized, and it's dependent on the frequency, and it's in multiples of the Planck constant here. So the other sort of basic idea to take into consideration is that electromagnetic waves, so we'll call it EM waves, have momentum, and so this we can say because energy is equivalent. I mean, it's equal to 1/2 mv squared, so we can just say it's equivalent to mv squared, and we know that momentum is equal to mv, and so from this, well, with energy, we say that v is equal to the speed of light. And so if we want to go from this to this, we can just say that p is equal to energy, which is mv squared, and we can actually call that c squared since we know v is equal to c. And then to make that, to get rid of one of the c's, we have divided by c. And so therefore we can say that p is equal to E divided by C, since this is the energy, and then, well, I mean, we know that energy E equals mc squared, so that's where that energy comes from there. And from above, we know that E is also equal to h bar nu, and so we can say that P is equal to h bar nu over C, and well, this is a relation I guess I could have pointed out earlier too as one of our sort of primordial or just known relations, that that c, the speed of light, is equal to the wavelength of light multiplied by the frequency of the light. And so we can say that nu, just doing a little bit of algebra here, is equal to c over the wavelength. And so from that we can say that p is equal to h bar 2 pi, and then c, which is from this, because we are substituting for this right here, so we have our c, and that's over the lambda here, and then we also have this other c here, so c, so these cancel out, and we end up with our p being equal to h bar 2 pi over lambda. And then we can actually set the 2 pi over lambda to pi over lambda, so because this is just a constant, then we are only, this is the thing that is varying. We set that equal to k, and we call this the wave number. And so you will see that come up a lot in quantum mechanics, this idea of the wave number, which is with this constant here, you can say is a, well, I mean, you could change the relation to say that 2 pi is equal to lambda times the wave number. And so you know that this multiplied by this is always going to be equal to this constant. But we know, because this is in the denominator, that if the wavelength increases, so you go from something with a wavelength like this to something with a wavelength like this, then k is going to go down. So these are inversely related to one another. And so from that relation, we can then say that that P is equal to h bar k, because we went through all this and the h bar stayed here, but we said that this part was equal to k, so we can say that P is equal to h bar multiplied by k, and this is what is called the de Broglie or de Broglie or de Broglie. I've heard it all these different ways, but de Broglie's relation. And so this is something you will see quite often in quantum mechanics as well. And so this is just telling us that the momentum of a wave is related to the k, which is the wave number. And so we know that since the wavelength is inversely proportional, so we could say inversely proportional to k, then if our wavelength is getting smaller, then our k is getting larger, and therefore our momentum is getting larger. And that makes sense if you also just understand the relation of momentum and energy, that energy is equal to the 1/2 mv squared, and momentum is equal to the mv. If this one's going up, then this one is also going up, and vice versa, because they have these same variables here. And we said that that the energy goes up when the frequency goes up. Since lambda is also inversely proportional to frequency, then we know, that should be an F, then we know that k is proportional to frequency, or you could even say k is proportional to the angular frequency here. And so we know that if the energy is going up, then the momentum has to be going up. We know that if frequency goes up, then the energy goes up, and so if the wave number goes up, then so must the momentum go up. And so that is the de Broglie's relation there. And so now we can move on and say that the relation of kinetic energy, which is what I was talking about up here, is the 1/2 mv squared. And in fact, I'll put kinetic energy for this here, since we're not talking about total energy yet. And so, since we know this 1/2 mv squared and this P equals mv, then we can also say that P squared, which that's going to be m squared v squared over 2m, so that's the 2 here, and then another m here, which is essentially saying m squared v squared over m. So we cancel one of those out, and that's just mv squared. But we can use this momentum here in our kinetic energy. And so from this, because we know that P is equal to this h bar k, then we can also say that this is equal to, since this is the P squared, we have to do h bar squared and k squared. So h bar squared k squared over 2m. So this is also our kinetic energy here. And then we can say that total energy, which I will just use in E for that, is equal to h bar squared k squared over 2m. Then we also want to add that potential energy, and as we saw in previous videos, that's often in uppercase V is used for that. And so from there, and so we know that this is also equal. So E is equal to the h bar nu, which is equal to, so this whole thing here is equal to the h bar nu. Forget about this here, because we know that the energy from up here was equal to the h bar nu. We knew that, well, we used the modified version of the Planck's constant, and then this here. And so we had hf equals the h bar nu, which was equal to energy. And so we know that energy equals this equals the h bar nu. I'll even add that into our box here. And so now what we're going to do is assume a plane wave propagating in the x direction. And so a plane wave is just one where it has, that looks really bad, so it's just a constant frequency, and that goes off to infinity and to negative infinity. So there should be negative infinity. And so a plane wave is just a wave that is the same over an entire plane, but it can be moving. So you could have this this crest here at time t0, but then that could have moved over to here at time t1, and so we can imagine. So this is our x coordinate here. So we imagine this plane wave propagating in the plus x direction, and so that can be shown in the relation. So we'll call that psi as a function of x and t, so as a function as this space and as it's moving in time. That is equal to the amplitude multiplied by e to the power of I, and then k, which is the k that we were using up here, our wave number. So k multiplied by x, and then minus our nu multiplied by time. And I've pointed out in previous videos that we know from what's called the Euler formula, that e to the I x, when you have this I in here, which is the imaginary number, so it's the square root of -1, that the Euler formula for this is cosine of x plus I sine of x. And so we know from this relation here that when we have e raised to the power of I multiplied by something, that gives us a wave. I'm not going to go through the derivation of all this, but just know that this relation here is so. I think maybe a good way to talk about it is to say that if you ever see the imaginary number in the exponent of e, then you know that it is a wave equation. You know that it is some oscillating function like that. And so that's one of the reasons you often see the imaginary number used in quantum mechanics, because we are always talking about waves. And so that's essentially what that is telling you. That's where that sort of often talked about Euler identity comes from, where e to the I pi is equal to -1, because if we have our unit circle here, then if x equals pi, then you are going to start from here, and you will go 180 degrees over to here, and that will be -1. And so that's where that comes from. Where if you had e to the I 2 pi, then it would come all the way back around, and you'd have +1. And so that's where that oscillating comes from. But anyway, like I said, we are going to use this plane wave here, and we are going to use this here for our plane wave, using our wave number and our angular frequency here. And so if we take the partial derivative of our function here, which I will just shorten to just use phi, but just remember that it's a function of space and time. So the partial with respect to this should be the respect to time here. So I'll start with time, and we'll essentially do the same thing with space, except we will be taking the second derivative for that. And I'll get into in the future why we use only the first derivative for time and the second derivative for space. But for now, I will just sort of assert that is the case. And so this is equal to the partial derivative with respect to time of our a times e to the power of I k x minus nu t. So we're taking the partial derivative only with respect to time of this. And so if you know your derivatives for e here, then you'll know that what we end up getting is minus I times nu, because with the e we're just taking the minus nu and the I down because this I is distributed over to here, down in front of the function here, and that will be multiplied by the a e to the I kx minus nu t. And so we can say that this is equal to minus I nu multiplied by our function here, which, like I said, just remember it is this relation. And so what we can then do is say that the partial derivative of our function with respect to time is equal to minus I nu and then psi. And so then we can rearrange this to say that nu is equal to 1 over minus I psi multiplied by the partial derivative of psi with respect to time. And then so this, because we can move this I up into the numerator, we can say that that is equal to I over psi times the partial derivative of psi with respect to time. And so, like I said, we will do the same using this same function here for the space, but for that we will be using the second derivative. So the second derivative of psi with respect to x, and that's the second derivative. And if you did the first derivative, what you would end up with is I k psi. And so if you take the second derivative, you are just multiplying this by another I k. And so you end up with minus k squared psi, because I times I is minus 1, and then k times k is just k squared. So we end up with minus k squared multiplied by psi. And then if we rearrange this again, we have k squared equals minus 1 over psi, then multiplied by the second derivative of psi with respect to x. And so now we have this relation where nu is equal to this, and k squared is equal to this. And then since we know that that E is equal to h bar nu, and nu is equal to the I over psi, partial derivative of psi with respect to time, then we know that E is equal to I h bar 1 over psi, and then the partial derivative of psi with respect to time, because we're just substituting this in for our nu and then adding this h bar here. And I've just kind of moved the I out in front of it here instead of having it over the psi there. You could also just have this I h bar over psi multiplied by the partial derivative of psi with respect to t. And since we know that that E is equal to h bar psi, which is equal to the h bar squared k squared over 2m plus v, which is what we discovered up here. So this comes from what we found out up here. And since we know that k squared is equal to this, then we can substitute that in for the k squared here. And so then we can say that E is equal to the h bar squared from here over 2m from here. Then we're substituting this in for that k squared there. And so that will be the 1 over psi multiplied by the second derivative of psi with respect to x. And so from this, because we have these two E relations, these two energy relations, we can actually set this equal to this. And so with that, what we will get is I h bar 1 over psi multiplied by the partial derivative of psi with respect to t is equal to, and this should have had a negative because we have a negative in here. And so this should have been a negative because this will be equal to negative h bar squared over 2m 1 over psi multiplied by the second partial derivative of psi with respect to x. Then plus v. I forgot to add that plus v. That we had that from up here. We had the plus v. So this should have also had the plus v on it, which, as I said before, is our potential energy. And so from here, if we want to get rid of these 1 over psi's, then we just multiply everything through by psi, and that will give us I h bar partial derivative of psi with respect to t equals minus h bar squared 2m multiplied by the second partial derivative of psi with respect to x plus v multiplied by psi. And so we see psi ends up in every part of this equation here, and this is our time-dependent Schrodinger equation. So we can look at this and compare it to what we saw up here. So we have the IH bar first partial derivative with respect to time. That's what we have here, IH bar first partial derivative with respect to time. Then we have the minus h bar squared over 2m multiplied by the second partial derivative with respect to x. That's what we have here. And then we have our potential energy there, which we have here. This just kind of factored this right here out and out of both of these, but you could see that this would go here and then this would go here, and we end up with the same thing. And so that is the, as I said, the derivation in scare quotes here of the Schrodinger, the time-dependent Schrodinger equation. And like I said, in future videos, I'm going to explain in a lot more detail what each of these symbols actually mean, sort of the physical interpretation of them. I will talk about the time-independent Schrodinger equation. I will show how you can generalize this to higher dimensions, because what we have here, so that's why in this they keep this what this is a function of. So it's a function of one dimension of space and of time, but you can get this as a function of three dimensions of space and time. And so I will show how that is done, and I will show some of the solutions to the Schrodinger equation in later videos. And so, uh, like I said, the next few videos will be focusing a bit on the Schrodinger equation, both time dependent and time independent, and some of the solutions thereof. And so we will get a good understanding. So if you weren't able to follow that well in this video, then I think probably by the time you watch all of the videos on the Schrodinger equation, then it will start making more sense, and you could come back and re-watch this video and it'll probably make more sense after that. And I mean, I am a self-learner for the most part on quantum mechanics. My background is biochemistry, so I didn't take very much physical chemistry. So I'm a self-learner on all this, and if you are like me, then it's nice to sort of watch and rewatch and read and reread things about this in order for it to start making more intuitive sense. So I believe it was John von Neumann, the famous 20th century mathematician, who quipped that nobody understands mathematics, you just get used to it. And so I mean, I kind of understand that, because a lot of understanding things like the Schrodinger equation and quantum mechanics is just sort of keeping yourself exposed to it over time, going to different sources, go watch other people doing videos where they might explain it a little bit differently, read books where it's explained a little bit differently, and over time it starts making a little sense. You get used to it, and you're like, okay, I think this makes sense to me. I can look at this equation and sort of know what this is talking about. So yeah, that's just a little advice for my fellow self-learners out there, that if you watch this video and you're like, that was kind of hard to follow, it didn't make that much sense, then it's one of those things where it's just like, look for other videos where people explain it, come back and rewatch this one, read, a few different books on the subject, and after a while, this will start just becoming sort of easy and second nature to you. And that's just sort of my advice on getting a good grasp of this material. But anyway, I will get off my soapbox here and finish this video. So I will see you in another video.